Okay, everyone, I think we've let a couple minutes go past 8 o'clock here. I'm going to go ahead and get started. Again, thank you very much for joining. I realize these are very interesting times that we're in right now. And I'm working from home, as I assume most of you are, but I am greatly looking forward to the opportunity to speak with you a little bit about the portable data acquisition systems that I am responsible for. My name is Greg Smith. I have that right on the PowerPoint here. And I'm the product manager for data acquisition systems at Link Engineering Company. I work out of our Plymouth facility, which is based in Michigan. And the data acquisition that I'm going to talk with you about today is called the VMAX 4000. And this is it's a portable, rugged data acquisition system. Link has produced this data acquisition system for about the last 5 years. We have a lot of systems that are out there in use with a multitude of different customers in many different regions of the world. The data acquisition has been very successful for us as well as an internal testing product that our testing groups are able to utilize and use some of the functionality that's available for it. The system is constantly evolving from a hardware standpoint. We are constantly adding new module types, additional functional capabilities, and certainly from a software perspective, we are constantly improving, adding new features, adding new capabilities, a lot of times based upon customer requests, as well as based upon internal requests that we have from our own testing groups that use this instrumentation. So the VMAX 4000 I consider to be much more than just a data logger. I consider it to be an integrated test solution. We're able to supply test scripting to the user. We're able to provide immediate feedback on operator performance through audio cues, through calculations performed on the screen when required. We are able to automate test reports. Our data acquisition system runs on ProLink, which is a Link proprietary software that is common across all of our equipment types. So from our brake dynamometers to aircraft dynamometers to test benches to our portable data acquisition system, the software that is used to run those different suite of equipment packages is common. So the nice thing from a user perspective is that as a user is using one piece of Link equipment, it is an easy transition to go to another piece of a Link equipment. Our data acquisition system is capable of accepting virtually any signal type. Signal types that we may not have available to us at this time certainly can be added as a customer request. So as I mentioned before, we are constantly evolving the product. We are constantly adding capabilities as required based upon user needs. Sample rates for our system, depending upon the signal type, can go as high as 51.2 kilohertz. Primarily, that would be with our NVH type signals that we use in many cases for detection of brake squeal noise, but many other NVH attributes are capable. Brake NVH is interesting in that we need to be able to collect up to 20,000 hertz, hence the sample rate being set so high for our NVH channels. Another unique feature of our data acquisition system is the ability to link multiple systems together. So we can have multiple VMAX racks, as you see pictured on the screen here, linked together to one PC to be able to log multiple different racks at the same time. Primarily, we use this a lot for advanced driver assist system testing, where we may have multiple test vehicles on a test track that we wish to have all of the data captured onto one PC so that there isn't any job of putting the data back together at the end of a test. As I mentioned before, we have a wide variety of use cases for our instrumentation, some of which I have listed below here. So as I had mentioned, ADAS testing is certainly one that we are using our equipment for, and that is the advanced driver assist systems. So things like your lane departure warning, forward collision warning, those types of tests, blind spot monitoring. I do have a slide that covers some of our capabilities with that further in the presentation. NVH, noise, vibration, harshness, is most certainly something that we use our instrumentation for quite frequently. Many of our customers are using that for as well. We have customers that are using that for brake judder evaluations, doing system response on a vehicle. Certainly brake noise are things that we do. NVH PassBy, so as a powertrain, engine, tire type of NVH test, that is certainly done as well. We have customers that are using our systems for emissions cycling or cycle profiling, where a vehicle must follow a specific schedule in order to condition components on the vehicle for emissions testing. Vehicle dynamics. Our system is also capable of being used for measuring BTV, disc thickness variation, which would be a brake rotor component measurement. Laboratory bench testing. The system is very well at home, placed inside of a vehicle, but is not limited to just usage inside of a vehicle. We can use this system for test bench applications. We do that both internally in our testing groups, as well as we have a number of customers that are using those for steering system testing, component testing, things of that nature. PassBy noise, I had mentioned this one previously under NVH. I have a slide that will cover some of that. And a large part of our customer base, certainly on our internal testing side, would be for foundation brake and anti-lock brake system, both development and certification testing. We use this product for that purpose quite frequently for a number of OEMs, tier 1s, tier 2s suppliers out there, as well as we have OEM customers and tier 1, tier 2 suppliers that are using it for the same. Some of the modules that we have available to us, I don't want to spend a whole lot of time going through these, but I'll give you a general idea of some of the input types that we currently have. As I had mentioned before, we are constantly evolving this product and adding to these capabilities. But for our system, our VMAX system, generally speaking, consists of at least a power module, this 4080 power module that you see here, and a PC of some type. And our recommended PC that we have the best success with would be this embedded PC solution. So this is an i7 computer that is built in directly into the data acquisition rack. Doing this allows us to have administrative capabilities with the computer. A lot of times when we sell systems to customers that use their own laptop or their own desktop PC, IT restrictions can really make it difficult to execute testing and to be able to interface with the data acquisition system at times, depending upon IT restrictions. The power module that you see here interfaces with the computer through Ethernet protocol. And through Ethernet, we are able to communicate with all of the modules that then get installed downstream of this power module. The power module has a couple of different interfaces to be able to accept some sensor types. We are able to supply CAN as well as serial data into this power module. But all of the other inputs that you would wire a sensor to, a thermocouple to, a digital input, things like that would come from these other modules that you see here. So we have a couple of different analog input. So things like a string potentiometer, a load cell, a torque cell, things like that are available to go through these analog inputs that you see. The 4010 analog input has excitation voltage capabilities, so we can power a sensor. We're able to read very small signals. We can gain up to 8,000, so we can read millivolt type signals. It has 16-bit resolution. We have another input module that's just a differential input. So if we have sensors that are already powered by an external source and we just want to read the DC voltage coming off of those, that's where this module would be handy. We have an analog output module as well, so we can control things with analog DC voltage. We have a thermocouple input module that you see here with up to 15 thermocouple inputs per module, and we have a wide range of different capabilities there. We have J, K, or T type that can be used. That is software selectable on a channel-by-channel basis, so we could have multiple different thermocouple inputs, thermocouple types going into this one module, selectable by software. It's worth noting as well that we can add essentially as many modules as required to build up a test. So if we have a need for 40 different analog inputs, we would simply want to use 5 of these input modules. If we needed 30 temperatures, we would just need to add 2 of these inputs. The nice thing about adding or subtracting modules, this can be done, literally on a test-by-test basis. There isn't any software configuration required when you add or remove hardware to the system. It will auto-detect that, which is a very nice feature. Then move on to the next slide here, show some of the other input modules that we have. Our NVH module, as I had mentioned previously, we can sample up to 51.2 kilohertz with this module. It has 6 inputs. We use these most commonly for ICP or non-ICP type transducers like microphones and accelerometers. We do have 24-bit resolution on this module, so it has a lot of capability. We have a pulse input module that we use for collecting things like wheel speed encoders, flow meters. We use this quite commonly to measure precision GPS for speed and distance for something like a stopping distance test. We have a CAN input module. As I mentioned previously, the power module has the ability to collect CAN. This provides the user a way to collect more than one CAN input device. And this module does have CAN FD, flexible data rate capabilities now. We have a digital input output module that we use a lot of times for bench tests, for dynamometer installs. I haven't seen a lot of usage for this on in-vehicle testing, but that certainly is a possibility and a capability as well. We have a power over Ethernet switch that we use almost exclusively for running lots of Ethernet-based type of signals. We have a video input module that communicates over Ethernet, and we actually have a 4-channel video input module that communicates over Ethernet. So if we have lots of these modules, it's important to have a network switching point such that we can get all of the Ethernet traffic back to the PC for logging. We also have a telemetry module that I don't have pictured here, but it is part of this system that we use for measuring rotating temperatures as well as speeds with the ability to measure those wirelessly. So we don't have to run any heavy cables through the window of the vehicle, through the door of the vehicle. We're not drilling holes. We're able to do that using battery-powered wireless transmitters and a receiver module, which is very, very, very handy. Our data acquisition system, as I had mentioned, uses the same software as all of our Link products, and RevData Plus is what we use for reviewing both raw data, summarized data, audio data, FFTs, video. And I've got a few different screenshots here that just show a little bit in how that works. In the upper right-hand part of the screen here, I have a test that I collected with 444 events that were captured. And for each one of those events, there are literally hundreds of different variables and calculations that can be performed on that just using the software as it's delivered. And there are easy ways to customize those and be able to generate your own equations or calculations that you want to have calculated basically as soon as the event is captured. In the case that we see here, I've got some basic information, the date and time, how long the event was, I've got an average deceleration. I could have minimums, maximums, mean fully developed decels. There's a multitude of different things that are available with the software as it ships standard. In the upper left-hand corner of the screen here, I have our raw data screen. And this is where we would look at our higher sample rate channel information that's coming in on a time basis. So as you'll notice here, I've got a number of different signals. I've got a speed signal, a couple of temperatures. I have a load cell, and I'm looking at all of this information on a time basis here. I also collected video with this particular data set. So you'll see I have one of our video modules with a video sensor pointed out the front of the vehicle, monitoring what the driver is doing. I can actually see what is going on with the instrumentation here as well, but I can see what's going on with the road environment. And I found this very helpful, even on testing where video may not be required, sometimes to help understand what it was that happened that would explain an anomaly in my driving style or my driving habit. And on the lower right-hand corner of the screen here, I have some of our audio data that was captured. So I've got a cabin microphone that I'm currently looking at, where I'm looking at a scaled dB output here, and I'm looking at that time-based, and as well as we have frequency-based information that revolves around our NVH channels as well. So we're able to look from 0 to 20,000 hertz in frequency buckets and make determinations on what the NVH characteristics were of a particular event that were captured. This software is supplied with any test system that Link provides. There aren't any licensing charges. We distribute this freely. It's a very powerful tool. Certainly from a graphing perspective, I really like RevData Plus. We can plot up to 20 signals on a chart at a single time. It's much more flexible than Excel, in my opinion, when it comes to graphing and to be able to analyze data very quickly. Another tool that we have for analyzing data, and we use this primarily for compiling test reports, would be our Excel Addin tool. So we have an add-in that installs inside of Microsoft Excel that allows you direct access to the data, and we can pull in summary information. So we can use functions that look very similar to standard Excel functions to bring in minimum, maximum averages of specific channels. We can bring in raw data information, and that's kind of what I'm doing in the screenshot that you see here. In the screenshot that you see here, I am bringing in time-based information, and the real data set is a couple thousand rows long. And I'm bringing in an actual speed channel, and then I'm bringing in some targets, and then I've got a deviation, and then I'm doing some calculations based upon that. And all that it took for me to be able to do this was really, I've got to just feed in a data path, and then where that data is located inside of that test. And then I provide that channel that I want to see the data come in through, and what unit I want it to be reported out in. So when I type this information in, it takes a couple of seconds, and I can bring in, 5 minutes worth of data that was collected, as you can see over on the right-hand side of the screen here. So this was an example of a emissions road cycle test that we were performing for a customer, actually developed for a customer, where they have a speed profile that they must follow. So a driver must accelerate a vehicle, staying within a minimum and a maximum bound, maintain for a certain distance, they slow down, they speed up. And as you can see here, I've got minimum and maximum targets in red, my actual speed trace in blue, and then I have small yellow dots that indicate anytime that the driver was outside of the allowable bounds. And as soon as this happens, we're able to quickly report back some different metrics based upon how the driver performed. How long was their run? How much time did they spend inside or outside of the bounds? What was their accuracy? Things of that nature. So our Excel add-in is a very powerful tool. We have, I've personally seen customers literally spend hours or days to put together a test report when using a tool like this, after you've created a template in a standard way that you would like to see the data, that same operation takes seconds to be able to put together. So I have a few slides here that will show some of the different use cases for our data acquisition. As I had mentioned at the beginning of the presentation, ADAS, or Advanced Driver Assist Systems, is one of the ones that we have spent a lot of time developing. Our internal test group has been conducting the type of tests that you see on the screen here, a wide variety of them. A lot of the standard ones that a lot of folks are probably familiar with that are becoming available on vehicles: forward collision warning, crash imminent braking, dynamic brake support, which are all designed to aid the driver in alerting the driver if there's an object in their direct field of, or their direct path that they're going to strike, as well as providing some braking assistance to avoid that. There's also lane departure, lane keeping, which is again centered around keeping the vehicle in the middle of a traffic lane. So as a driver is not paying attention and drifts out of the lane, steering corrections or alerting systems are used. Blind spot detection, which is not a new technology, but that is something that we are testing for, and is becoming standard on many vehicles. Rear automatic braking, which is something that I do have a short video example of that I will show here. Certainly, as well as being able to monitor these while we are driving on public roads or on test tracks in more of a standard driving, and then looking for false detections or missed detections when events like this happen. And a recent test that we've actually adapted our instrumentation for is this adaptive driving beam, which is a headlamp or headlight test or headlight technology, I guess I should say, where the driver of a vehicle can have essentially high beam headlight performance without blinding. So the nice feature about this technology is that as you're driving down the road with your high beams on, essentially, as a vehicle is approaching you or you're coming up behind a vehicle, the headlight technology will dim itself around that vehicle so that the other driver's view isn't obstructed by your bright lights. So the screenshots that I have here would be what our data acquisition system, our VMAX, is collecting, and what the driver has accessible to them while they're actually executing their testing. So the video feeds that you see here, we have 4 separate cameras that are being recorded by our data acquisition system. We have one that is showing driver inputs. We have one that is zoomed in on the instrument panel of the vehicle so that we can see alerts as they become available to the driver. We have one mounted on the roof of the vehicle so that we can see the object that we are backing up towards, hopefully that we will not strike. In this screen that you see here, this is inside of RevData Plus. So this shows a picture of the vehicle, an outline of the car, as well as the object that we are backing towards. And this is animated when we are viewing that inside of our RevData Plus software. And based upon time, we can see all of the other signals and things that are going on, as well as the vehicle's relation to the object. The screen that you see directly below this would be the driver interface screen that the driver would use to execute this test. So the screen that we see here is really developed specifically for this one test. And adding these different screen objects and these different channels and things like that is very easy, is very customizable, and that's something that we frequently do as a support service for our customers, as a demonstration when we want to go show new functionality. Those are things that we can quickly and easily adapt to multiple different testing types. Over on the right side of the screen here, we have one of the tests that we conducted, and this is just a sample test report that shows some raw time history of what was happening, You can see that we have a blue line here where the vehicle is driving, and then we see the vehicle slow down. We have a haptic feedback. This green line that you see here is when an audible warning was alerted to the driver. And you can see basically as that happened, that is when the vehicle started stopping itself. And this was to avoid hitting the balloon car that you see here. So I have a short video that will show. So in this video, it will show essentially a rear automatic braking test. So as you'll notice, I'm going to pause this briefly here. As you'll notice, as the driver is approaching this child mannequin here, you'll see that the driver interface is updating. So we're looking at time to collision. We're looking at the vehicle's lateral offset as it relates to this child pedestrian, which is one of the attributes that the driver must control during this test. We have the video feed that the data acquisition system is collecting here, these four videos, as well as we have the animated Rev Data Plus that we are screen that shows the vehicle and its relation to the object as well. So we'll notice there that the indication to the driver that there was a imminent collision there was illuminated, and then the vehicle actually braked on its own. The next test is a automatic emergency braking test. So we have a test vehicle here, and we have a balloon car here that is being pulled by another vehicle on a special trailer. And the balloon car, if it is struck by this vehicle, sustains very minimal damage to both the test vehicle as well as the balloon car. And again, this is a similar arrangement to the last one here. So you'll notice that, I'm going to pause this briefly here. You'll notice that we have some different attributes that are now displayed on the driver interface screen. We have, again, some offsets. We have speeds, and there's a speed target that both the driver of the balloon vehicle as well as the driver of the test vehicle must maintain. And then the driver of the balloon car must brake at a specific deceleration, and then we are looking at all of these things real time. So it's without the aid of a lot of the channels that we've added here, it can be a very difficult test to execute based upon the precision that is required to orchestrate all of this. As you'll notice, we do have a camera that is mounted here on this trailer pointing back at the balloon car, and this is connected inside of the pull vehicle, this truck here, and it's being wirelessly transmitted back to the test vehicle that you see. You'll also notice at this time that the forward collision warning or the crash imminent braking detection system has alerted the driver that there's an issue, and then the vehicle is going to begin braking. So I'll back this up a little bit and then just let that play. So moving on to a different application type, we have used our VMAX 4000 for NVH PassBy. And this is kind of an interesting test in that we do need multiple data acquisition systems, or we need the ability to collect sensors that are not just on the vehicle. So it's very advantageous for us to be able to have sensors that are wired inside of the vehicle, CAN information coming from the vehicle for things like vehicle speed, throttle position, engine RPM, things of that nature. But at the same time, what we really need to know for a test like this is what are the sound pressure levels, what are these sound level meters that are mounted on each side of the test course reporting as the vehicle drives through. We do have a wind anemometer that is mounted here, as well as a camera. So we have, in this particular arrangement, we have a data acquisition system that is mounted in the vehicle with a PC for logging, with an embedded PC that you see here. And then we have two more data acquisition systems that are mounted on the, so it's very quick and easy to set up. The two systems that you see mounted on the side of the track do not have a PC with them. They are wirelessly transmitting their video, their sound pressure level, their ambient temperature, wind speed data, all back to the vehicle. And all of that data is being logged into one data set. So in this example, we have 3 different data acquisition systems that are all logging to a single PC for seamless time synced data, which is very convenient. As you'll notice, the driver interface screen that you see here looks a fair bit different than what we saw for the ADAS testing. And as I had mentioned before, adding these different objects to the screen, these different channels, these different particular points of interest is quite easy to do. I do have a short video that shows the NVH PassBy. Go ahead and click play on that. So you'll see here the driver interface screen, the driver's controlling their speed. They come through and they must go wide open throttle. And then we are measuring the dB levels. And immediately after the run is complete, we have data available both to the driver as well as to a witness agent that is standing on the side of the track there who's able to see this information live as well. So we're able to verify that the driver has went wide open throttle by the time that they need to, and that all the other parameters have been met, and then we can evaluate the sound pressure level performance based upon whatever the requirement is that we are testing to. Moving on to the next application, this kind of demonstrates our ability to be able to script to the driver in a real-time type format a multitude of different attributes or signals that they need to try to match. This testing that I'm going to show here has a few different things going on the driver screen that you'll see, as well as it has some audio prompts. I'm hoping that my speakers and everything will work such that you can hear that. But on the driver interface screen that we see here, we have a speed profile, and this is similar to what I showed you in one of the data examples earlier, where we have minimum and maximum targets with an actual speed trace coming from the GPS sensor on the vehicle. And then I've got a series of different target bars here. I have a braking target here. So the one to the left in this teal color would be a target, and then the yellow right next to it would be whatever the driver's actual input is that time. I have a similar target bar for throttle. So as you'll see in this particular example here, this is the throttle target. This is the throttle that the driver is currently applying. And then I also have a park brake on or off target. So as this becomes illuminated, that would indicate to the driver that they need to apply the park brake. And as this is not illuminated, that would indicate to the driver that the park brake should be off. And in doing this, really all that's required is that we put together a Excel file, a CSV file that shows a time history of what we would like to display to the driver. So we can pick from any channel, anything that we have access to with this data acquisition system can be displayed to the driver in the type of format that I'm showing you. It could be steering, it could be, it doesn't have to be throttle and braking, it could be anything on the vehicle that we can then assess its objective performance based upon a sensor or a piece of CAN information.
Release park brake. Excel. Now.
So you'll notice I have a throttle input. So I'm doing my best to match this, also following a speed profile here.
Brake. Now.
So I have audio feedback telling the driver that they need to brake. This is the brake target. This is the braking actual signal here.
Apply park brake. Now. Idle for 10 seconds.
So that was just a very short example, but it shows that we can script what we want the driver to be able to do. So we can provide audio prompts to the driver, which can make it much easier to execute a test without staring at a screen. We can also provide audio feedback to the driver if they aren't doing what they should be. So if the driver is going too fast, we can simply tell them to slow down. If they're going too slow, we can obviously tell them to go too fast. And all of these things are customizable. Really, the sky is kind of the limit there, and what could be done really just depends on what the specific application is that a customer of interest would like to use it for. The next example that I have uses a piece of software that we call VSI2, which is Visual Script Interface. And for any of our customers that are currently using any of our dynamometers, this is probably pretty familiar. This piece of software has been used traditionally on our larger pieces of equipment to actually control the machine. So you specify how fast you want the machine to spin up to and at what temperature you want it to make a brake application and to what torque level you want it to do that. We've adapted this to be able to be used with our portable data acquisition system. And what we're using it for in our portable data acquisition system would be to prompt the driver what they should be doing. So in the example that I have here, this is a noise matrix that was being conducted. So I have a customer who came to us with a very difficult test that they must execute. It takes them about a week to perform it. There are about 5,000 different applications that they must do, events that they must record, and each one of them is different than the last. So as you'll notice on the screen here, I have the first event that they want to capture. They need to drive the vehicle in a forward direction at 5 kilometers per hour. And at an initial brake temperature of 20 degrees Celsius, they need to apply 0.1 G deceleration. And then you'll notice on the second event, they're going in reverse and they have a different application level. And then on the next event, you'll notice that they have to transition over to a pedal force control. So they're no longer controlling deceleration. So in this software, we give the user a pretty easy way to be able to script out a test, to provide audio prompts to the driver, to change their screens that they're looking at. So we can change their logging parameters. We can change what the target bars are that they see. We can change the application levels. So all of those things are possible to use in this VSI2 script, which is pretty convenient and pretty intuitive. Right mouse click, you can add a column, you select what it is that you would like to have that you would like to control, and then you enter that set point. This software does work with Excel as well, so you can actually build a test matrix in Excel, and then you can copy and paste back and forth with it. So I will have a short video on this one as well.
At 20 degrees C, drive reverse direction. At 3 kilometers per hour, target decel is 0.20 G.
And then right after the driver executes that stop, we automatically launch this subjective rating screen where they would like to enter in their subjective rating comments. In the past, they were writing this down on a piece of paper, and at the end of the test, they would spend a couple of days entering in these 5,000 different events worth of subjective comments and formatting that all nicely. So what we're able to do here is we're actually capturing a couple of different ratings, a squeal rating, as well as a groan rating. And then we're also asking the driver to identify if they understand where the noise may have been coming from. Was it a front axle, a rear axle, both? And then they're describing what the noise type is. And all of this is captured in our data and is easily accessible in software programs like our RevData Plus, as well as our Excel tools, where we can bring this into a template for a final test report.
Select rating before you click the Apply button. At 30 degrees C, drive forward direction. At 20 kilometers per hour, target pedal force is 200 newtons.
So you'll notice here on the previous application that I performed, we were controlling to a deceleration level. And then as soon as I launched this new event here, it has now changed my target bar to be pedal force. It's changed its application level. My targeted speed is very different. The target that I see on this speed dial has been changed. My initial brake temperature has changed. So again, the screen that we're looking at here is fairly basic in nature. This is what the customer wanted here, but this can look like anything that is required. We can add as many signals. We can add bar graphs or bar charts like this, speed dials. We can add set points. There's a lot of interesting things that can be done to make it easier on the operator of the equipment, where they can spend more time just driving the vehicle and paying attention to the objective performance of the vehicle, so that they can rate it, as opposed to trying to change things on the data acquisition system.
Select rating before you click the Apply button.
So that covers the VSI2, the scripting interface. The last sort of application that I have here, and I don't have a video on this one, my apologies, but another interesting thing that we've used our instrumentation for would be to collect DTV data. DTV is disc thickness variation, and is an important attribute for braking performance, braking durability, braking warranty. But the couple of photos that I have here show some different options that we have available to us. And essentially, to take a measurement like this, you need precision distance measuring devices. So we commonly use a no contact capacitance probe. The particular example that you see here is a micro epsilon system. And this system has some built-in signal conditioning and things like that. And it actually communicates to our data acquisition through Ethernet. And we also have an encoder here that will very precisely measure the angular position of this wheel as it is spun, so that we have an understanding of lateral mounted runout and disc thickness variation as it relates to angular position of the rotor that we are measuring. And in this example here, this encoder is also Ethernet based, and it is being connected to this Ethernet module that you see here. So this is a very portable solution. As you can see, the components that are required for this are all quite small. This would very, very easily fit into a small carry bag. This is similar to some of the other larger test stands that we build for sort of a permanent install in a garage or on a test bench. But it really gives the user the flexibility to be able to take a measurement like this out in the customer field, where taking a larger piece of equipment like that might not be possible. The other interesting thing about that is that this is the same data acquisition that could be used for ADAS testing, or PassBy, NVH, or a brake test. Any of those. It's not a completely different specific piece of data acquisition. It's the same core data acquisition with a couple of different sensors being interfaced with it. And in this example here, this is micro epsilon. There's certainly many other systems that could be used. Capacitech is another one that we use quite frequently. Still could be Ethernet based protocol. Certainly could be an analog output that we send into an analog input module for reporting. Same holds true for sensors like this encoder that you see here. And the last thing that I have here is a simulated driving software add-in that we that we've been developing. It's actually been pretty useful since I have been working from home now. Currently, at least in my state, driving on public roads really isn't allowed unless you are going to an essential store or something like that. So some of the testing that I've been able to do in the past for looking at logging configurations and things like that hasn't really been possible. So we have a software add-in that will take certain signals being interjected into the data acquisition system, and then it can generate other signals. So for example, I'll start the video here.
So if you notice,
in this video here, I have a few different things going on. I have a steering wheel with a shifter, a gas pedal, and a brake pedal that are being used to simulate other channels, such as engine speed, vehicle speed, acceleration or deceleration, braking temperatures that you'll see that will increase, that will cool off. And what I've done here is I've put together, it's just a short drag race simulation, but it shows that you can drive the vehicle with a couple of different sensor inputs. And I've actually found this very helpful for testing out logging parameters, testing out other functionality that we're developing just by being able to essentially virtually drive the vehicle without actually being inside of a vehicle. So I'll go ahead and play this video here.
my screen here, the lower dial, you'll notice that I've got a steering angle that moves back and forth. I have a throttle input, as well as I have a shift light LED that comes on at 6,500 RPM. I have a brake input here, and then I've got a couple of different buttons. This is a trans brake. This is a parachute. And then I have the ability to shift the vehicle up and down. So you'll notice at the top of the screen I have gear 1, gear 0 is neutral. And on the right side of the screen I have brake temperatures. So you'll notice that at the end of the run, as I apply the brakes, we'll actually see brake temperatures increase. And I will apply full throttle. So you'll notice I have a shift light LED that's coming on now. And I'm going to go ahead and start logging. As the tree comes down, I'll let go of the trans brake.
As you'll notice there, I've simulated a drag race Christmas tree here, and I have some real-time information that's being displayed. So I have a reaction time, which is negative. I actually took off too soon. And then I'm reporting out, 60-foot, 330-foot times, as well as some elapsed speeds and times for both the 1/8 mile and the 1/4 mile, which is a common attribute to report based upon a drag race run. And as you'll notice, as I went through, engine speed would go up to red line, to where I had a shift light coming on, being controlled by our data acquisition on a digital output. I would shift the gear, it goes into the next gear, and vehicle speed increases. And then at the end of the run here, you'll see as I start braking, you'll see temperatures increase. Meanwhile, I was playing an audio file.
Pull the vehicle down, we'll notice that we have temperatures increasing over on the right. I hit the parachutes, and I stop very fast.
So that's just a little fun that I had with a driving simulator. And again, it's actually been quite helpful in proving out a lot of the different things that we've been working on. So at this time, that's what I have prepared for the presentation. I certainly appreciate everyone's time. I had really excellent turnout. Really glad that everyone could join today. I hope everyone is staying as safe as they possibly can.